I can start introducing it, and then I guess people will filter in. Yeah, I think we have starting to get there. All right. Yeah. So it's a pleasure to have Dr. Philip Brydon here today, giving us the Monash colloquium in collaboration with Fleet. So actually, I know Philip from quite a few years ago. We both did our undergraduate degrees together at ANU in Canberra. And Philip went on to do a PhD at the ANU before going on to Germany and doing postdocs in Stuttgart and in Dresden, and then in the US at the University of Maryland with Shankar Dasama, before finally joining the University of Otago in 2015 as a lecturer. And so today, so Philip is an expert in particular in unconventional superconductivity. He's a condensed matter theorist, and so he will be telling us some very interesting work that he's recently done in this area. So look forward to it. Philip.
Okay, thank you, Mira, for the introduction and for the invitation to give today's colloquium talk. It's not the first time I've given a Zoom lecture, as most of you can imagine, but it's the first time I've given a Zoom colloquium. So please do forgive me if my jokes fall a little flatter than normal. Anyway, so the topic I'm going to talk about today is basically my some research I've been doing over the last 4 years, which evolved in a rather unusual and fascinating way. For people in New Zealand, they've probably heard most of this already, but nevertheless, maybe this time the talk will be slightly better. So to begin with, I'd like to I have to thank my collaborators. I've had a number of people joining me on this in this research. In particular, I'd like to mention Daniel Agterberg from the University of Wisconsin, Milwaukee, and Carsten Tim, who was my postdoctoral supervisor in Dresden, who has also been very strongly involved in this work. And there's also some notable mention of PhD students, Han Gyo Su, again from the University of Wisconsin, and my own PhD student, Henry Menke, who has just completed recently. And this work has recently been funded or has been supported by the Marsden Fund, so I'd like to acknowledge and thank them for that. And just to flash up some information here at the start, the talk will be based upon essentially mostly these 4 papers. So in the first paper was some work I had already been doing at the tail end of my time at the University of Maryland. And then the main topic is really discussed in these following 2 papers. And if I have time, I'm not sure that I would like to say a few words about some of our most recent research, which has just been published in Physical Review Research. So let's begin at the beginning. And for superconductivity, that is in 1911, with the discovery by Kamerlingh Onnes of superconducting state in elemental mercury, with a TC of 4.2 Kelvin. And this, I believe, is the original published data. So essentially, what Kamerlingh Onnes discovered in mercury and subsequently in many other elements and other compounds is the essence of the superconducting state, or what we normally think of when we think of superconductivity. And that is that we have an electrical current flowing without any apparent resistance below some critical temperature. And this drop-off of the electrical resistivity, as you can see, is actually quite abrupt. It doesn't continuously go to 0, but it just essentially drops to 0 at some particular critical temperature. Now, the other side of superconductivity is the Meissner effect, which was discovered in 1933, which is the observation that within the superconducting state, that magnetic flux is expelled by the superconductor. And together, actually, these two observations essentially form the physical basis of our understanding of or characterization of the superconducting state. Now, as I've said, the superconductivity research has been going on now for well over 100 years. And we now have quite a menagerie of different superconductors that we understand. And as you can see from this rather peculiarly scaled chart, there's been, at least from the 1980s onwards, there's been something of an explosion of interest in superconductors and a realization that they can appear in many interesting and different materials. In particular, I would like to draw your attention to the fact that in this graph here, only the green dots correspond to superconductors where we can really be said to understand what is going on. All the other materials, these green stars, the red triangles, the purple triangles, these blue diamonds, and most recently the iron pnictides with these orange squares remain quite controversial. Now, of course, the dream of superconductivity research is to discover a superconductor that will superconduct with a critical temperature which exceeds room temperature. And if you've been paying attention, you might have noticed that there's been recently a Nature paper which claims to have discovered superconductivity in a hydrogen-rich compound at a temperature of at least 16 degrees Celsius, which is quite an achievement. But the catch, there's always a catch, is that although the temperature is quite mild, the conditions remain quite extreme. So this particular compound seems to be related to this material, hydrogen sulfide, which superconducts only at extraordinarily high pressures. And unfortunately, our room temperature superconductor is also in the hundreds of gigapascal range of pressure. Anyway, this explosion of, or this onwards march of the critical temperature of superconductivity to higher and higher values has also been accompanied by a realization that superconductivity can be put to quite a variety of important applications. So perhaps most importantly, superconducting magnets. We probably most likely would encounter that in an MRI machine. However, there are maybe more speculative approaches, ideas to involve superconducting magnets in maglev trains, most recently also in wind turbine generators. And if you happen to work at a particle collider, the magnets in the particle collider will undoubtedly be based on superconductors. Now, unfortunately, the idea, it might seem like a very nice idea to use superconductivity to carry electricity without resistance over very large distances. But so far, this has kind of run into the problem of dealing with the low temperatures. And so, although there are proposals for electrical cables and some test implementations, these are not so common. I'm going to skip over this because it pretty much says all we have to say on the subject. But also, superconductors are maybe finding the application in squid microscopes, and most recently, and perhaps also controversially, in quantum computers. So let's now move on and talk about our theoretical understanding of superconductivity. So although it was discovered in 1911, it wasn't until 1957 that the first truly microscopic theory of superconductivity was proposed by Brydon, Cooper, and Schrieffer. And what their understanding of superconductivity is really quite remarkable. So essentially, the idea is that we have the electrons in the crystal have attractive interactions which are mediated by the phonons or the crystal lattice vibrations, which the existence of these attractive interactions leads to the formation of electron-electron quasi-bound states, the so-called Cooper pairs, which ultimately are the building blocks of the superconducting state, and which I am going to represent schematically by this little cartoon picture here. Now, the size of the Cooper pair is actually generally pretty large compared to the size of the crystal lattice. It can be anywhere from 10 to 1,000 nanometers in its in diameter, so to speak. Or and as such, you would there is generally typically a very large overlap between many different Cooper pairs. And so the wave function of the electrons in the superconductor realizes a coherent state of these objects. And it is therefore the details of how the electrons bind into this object, the Cooper pair, that controls the properties of the superconductor. So let's take a somewhat deeper look at this. So the picture of the Cooper pair is actually quite similar to, well, the hydrogen atom problem that we're all familiar with from elementary quantum mechanics. Essentially, we have two spinful particles which are forming some kind of bound state. And we know from the hydrogen atom problem that we can typically characterize these, the wave function based on good rotational quantum numbers. In particular, we have an angular momentum state, the total angular momentum and the azimuthal component. And we also have the total spin angular momentum of the particles. And of course, it's also its azimuthal component. But in building this the wave function of the Cooper pair, we have to be mindful of a very important point, which is absent in the theory of the hydrogen atom, specifically that the electrons are indistinguishable spin half fermions, and therefore the overall wave function of the electrons must be antisymmetric. What that means is that if I exchange the positions and the spins of the two electrons in this Cooper pair, the wave function of the Cooper pair will pick up a minus sign. That is quite a restrictive condition, and in particular, we can see how it is satisfied in the BCS theory of the Cooper pair wave function. So they proposed a Cooper pair wave function, which I'm representing schematically here. So we have the electrons in a relative S wave. So that means that we have L equals 0 state for the orbital component of the electrons in the Cooper pair. And we have them also pairing in a relative spin singlet. So if you look at this wave function, you can see that the antisymmetry, the fermionic antisymmetry, is going to be realized in the spin part of the wave function. If you exchange the labels 1 and 2 here, it's quite clear that the overall wave function will pick up a minus sign. On the other hand, the S wave orbital wave function is even under exchange R1 to R2. So how do we actually see this wave function, or the consequence of this wave function, in the superconductivity itself? So again, let me jump back to elementary solid state physics, and let's consider a very simple model of a metal, where we have some kind of dispersion here. And we know that we are filling up our electronic C up to the chemical potential, up to our Fermi energy mu, which corresponds to some maximum wave vector Kf. And this defines for us a Fermi surface. So in other words, the Fermi surface is a surface of zero energy excitations, or or an isoenergetic surface in the momentum space corresponding to states with zero energy. So all of the states inside of the Fermi surface will be occupied and the states outside will be unoccupied in the ground state. Now let's switch on the superconductivity, and we find that the picture changes quite dramatically. Most importantly, we open a gap in the dispersion. So essentially the electrons that form the Cooper pairs would typically come from close to the Fermi energy itself. And this will destabilize the electron states in the vicinity of the Fermi energy, thereby opening this gap in the excitation spectrum. Now, as such, the Fermi surface is essentially gapped out. There are no zero energy excitations left anywhere in our crystal, or zero energy electronic excitations, I should say, in the crystal. And the gap in the momentum space is essentially proportional to the angular momentum state of the Cooper pairs. So in this case here, we have a S-wave pairing. We have a L equals 0 angular momentum state, and this corresponds to a uniform gap over the Fermi surface. Now, we can evidence this quite nicely, say in most clearly in something such as the specific heat. So if we examine the specific heat, due to the presence of the gap, we will expect that there will be an activated behavior of the specific heat in a superconductor, because it will cost some finite amount of energy equal to the gap to excite a particle from one side to the other. And this is indeed observed very nicely in many superconductors. So in this particular material here, rather improbably barium-8 silicon-40, which is really the only nice graph that I could find. What we can see here is that at the critical temperature, there is a sharp jump in the heat capacity, which indicates the second order phase transition into the superconducting state. And now the heat capacity deviates significantly from the linear in T dependence that we would expect from the presence of the Fermi C. And at very low temperatures, it will go clearly exponentially to 0. Okay, so what about...
Oh, sorry, Philip, you have a question from Alex.
Yes?
About the dispersions in the chat.
Okay, wait a second.
It's always painful to access the chat for the person presenting, so I just didn't want to interrupt you. But my question was, for ordinary metal, your graph on the left, you just have a quadratic dispersion curve, and you've just got a single value, right?
Yeah.
And when you go to the superconductor, you've got the quadratic dispersion curve anti-crossing with a second quadratic curve. And I'm wondering what the origin of the hole-like dispersion curve is. Why is there a hole-like dispersion curve above mu? Is there a simple explanation for that?
So there is a mixing, well, probably not a simple explanation, really. I mean, how simple do you want? What I have illustrated here is that we have you'll notice that there is a shading of the dispersion. So the dispersion is shaded according to the electron-like content of the wave function corresponding to this energy solution. So in other words, there is a mixing of the electron and the hole-like excitations in the vicinity of the superconducting gap. And this is essentially coming from the fact that we are no longer, I think you could understand it in the sense that we are no longer conserving particle number in the from the point of view of the electrons, that the electrons are essentially dropping in and out off to the Cooper pair condensate as Cooper pairs are created and broken.
But at k equals 0, where I'm away from the anti-crossing,
Mm-hmm.
I've got well-defined, according to your shading, I've got well-defined electron-like states below the chemical potential and well-defined hole-like states above the chemical potential.
The mixing is greatest in the vicinity of the superconducting gap, in the vicinity of the Fermi wave vector.
But
as one moves
why do
away
I
from
have
the
hole-like states above, even at k equals 0? Why do I have well-defined hole-like states?
well, I guess you always have well-defined hole-like states. Okay, so this is the this is not a hole-like band. This is not a this is not a hole-like band in the sense that one might have a hole band in a semiconductor.
No, this is a whole band of just missing electrons band, right?
Yes, essentially.
They're anti-electrons. But yeah, okay.
Okay, so
Right.
sorry about that.
Yeah.
Okay, so let's continue now and look at the question of maybe explore the consequences of the angular momentum of the Cooper pairs. So let's consider the simplest possible choice here, where we have an angular momentum state L equals 2. And essentially in this very cartoony picture here, we have the azimuthal quantum, essentially an azimuthal quantum numbers plus or minus 2. So we have electrons, a superposition of Cooper pairs rotating to the left and rotating to the right. And in particular, in the way that we combine them, we would expect to get essentially a D-wave form factor for the orbital component of the angular momentum state. So essentially, this is nothing but the spherical harmonics corresponding to the superposition of the L equals 2 LZ plus and minus 2 states. And of course, this is in this state here will also not change sign if we swap the positions of the electrons. And so the anti-symmetry is again encoded in the spin state of the Cooper pair. Because of the higher angular momentum of the Cooper pairs, we now find something rather remarkable in the dispersion. So in particular, the gap remains proportional to the angular momentum part of the Cooper pair. And as we can work out quite straightforwardly, the gap will vanish along the directions kx equals ky and kx equals minus ky, which will lead to line nodes of the gap. Essentially, if we look at our Fermi surface, we are not completely gapping out our Fermi surface anymore, but rather there will be line nodes along the intersection of the Fermi surface with these planes, where essentially the Fermi surface remains intact. We are only partially gapping out the Fermi surface now. An example of this, a very well-known example of such a pairing state, is the Cuprate high temperature superconductors, which are the superconductors which have the highest critical temperature at ambient pressure, up to 150 Kelvin or more. Now, these materials are all essentially related by the existence of copper oxide planes within the material, hence the name cuprate. These copper oxide planes are separated from one another by generally quite far distances in the crystal. So the material becomes very quasi two-dimensional in its electronic properties. So we can essentially drop the Z component of the momentum and imagine that we have essentially cylindrical Fermi surfaces, which I show as these dark lines here projected into the Kx, Ky plane. And on top of this, I show the gap of the proposed dx squared minus y squared wave gap, which is known to exist in the cuprate materials. And you can see there is a sign change. As we move around the Fermi surface, there will be a sign change of the gap. And consequently, there will be these points here where we have a node appearing. Of course, these might seem like nodal points, but in fact, they are nodal lines, bearing in mind the fact that we have this third dimension coming essentially out of your screen, and we have these cylindrical Fermi surfaces. So we can actually directly image these nodes using modern photo emission technology. And this is absolutely beautiful experimental results for one of these bismuth-based compounds, bismuth 2212. And you can see very clearly that we have this this nodal gap appearing in the essentially at the diagonals at this angle 45 degrees. And in this combined momentum space and energy cut, you can very nicely see these low energy excitations existing all the way up to 0 energy, corresponding to the...
I have a question.
Yeah.
Philip, so it looks like that you have double degeneracy for the possible order parameter. What I mean that the horizontal is blue and the vertical is red. You could probably have the inverse one.
Yes. Okay. So that is there is of course a gauge degeneracy of the superconducting state. Essentially, just like any good wave function, you have the possibility of multiplying it by a phase factor. So you could, of course, talk about swap the red and the blue by multiplying by an appropriate phase factor. But essentially, we can just set that phase quite arbitrarily and happily to 0 for our purposes. Does that answer your question?
Yeah, thank you.
Okay. So the other point here to make is that, of course, we didn't have to wait for more than, I guess, 30 years to be able to image the superconducting gap. We could already have worked out that we would have line nodes simply by looking at the heat capacity in this material. So in this plot of the heat capacity in some of these Cuprate superconductors, you can quite clearly see that we have a T-squared, characteristic T-squared heat capacity at very low temperatures, which should be contrasted with the exponential dependence that we had in the superconducting state. Oh, no, in the S-wave state, due to the existence of these low energy excitations. Now let's talk about something a little bit, now let's talk about what would happen if we were to throw away one of these rotating Cooper pairs. So we only have Cooper pairs rotating in one direction. So that is, we are going to isolate our Cooper pairs with LZ equals 2. We're going to no longer talk about the superposition of our quantum numbers. And in this case, the gap is just a spherical harmonic L2, LZ2. And we find that this gap does not have line nodes, but now it has point nodes. So if we are going along the direction kx equals ky equals 0, in other words, the kz axis, we would find that along this direction, the superconducting wave function is vanishing. And we now have these point-like point nodes, which are the remnants of our Fermi surface. So I've essentially now summarized the 3 types of superconducting gaps that we believe that you can have in a material. So you can have the full gap, as we've seen from the BCS theory. You can have line nodes, which exist in the high TC cuprates. And you also have point nodes, which can exist in a material where, for example, we have this essentially a angular momentum polarization of the Cooper pairs. And for many years, it was believed that this is all that you could possibly get. And one thing I'd like to point out here is that there is something here which is maybe we're missing something. That we have a point in our three-dimensional space where we have a zero energy excitation. Here we have a line in our three-dimensional space rather, where we have a zero energy excitation. But we don't have a surface in our three-dimensional space where we have zero energy excitations. So with that, let me move on and somewhat switch gears a little bit and ask the question, what if we decided that we wanted to play with electrons which had a higher spin, say spin a half, higher than spin half? Well, this isn't a particularly crazy idea, really. I mean, we can, nowadays it's quite routine to make cold atomic gases of fermionic atoms. They can be made superfluid. And in these materials, typically the role of spin may be played by the hyperfine spin index. And so theoretically, it would be possible for us in these materials, such as sodium-22 or cesium-34, to form Cooper pairs with total spin up to 5 or 7. Of course, that doesn't, as far as I'm aware, there aren't any experiments which show this, because the experiments are generally conducted in a manifold, submanifold of the hyperfine spins, so that essentially we're effectively dealing with a spin 1/2 problem. But the possibility is still there. But what relevance does a higher spin have for the solid state? So let's talk about where this might appear and go back to essentially basic atomic physics. So if we wanted to write down a general Hamiltonian of a multi-electron ion, we can write down the single particle Hamiltonian for each of these electrons. But then we also have a number of other terms that we can deal with. So we have the residual electronic interactions between the electrons, and we also have a spin-orbit interaction. Now, it turns out that one cannot treat the Hamiltonian with both of these terms, H1 and H2, exactly. So we have to treat one exactly and use the other as a perturbation. And some guidance here can be given by the fact that the H1 term should scale as essentially the atomic number Z, whereas H2 might be expected to scale as the atomic number to the power of 4. And therefore it brings us to essentially two ways of thinking about our classifying the electron states in an atom. In a light atom, essentially we can treat the azimuthal quantum angular and spin quantum numbers of the electrons as good quantum numbers for labeling our single electron states. In a heavy atom, however, we can treat the total angular momentum. We must treat the total angular momentum of the single electron states as our good quantum numbers. And that's going to be because the angular momentum and the spin is locked by this very strong spin-orbit interaction. So just to give you an example of how this might work, in the total angular momentum basis for a heavy atom, essentially we will write down our states not in terms of NL, ML, and MS, but rather in NL, J, and MJ, where J will take the value of L plus or minus a half. And a nice example of this is provided by the J equals 3/2 states that we can construct by combining a p wave-like orbital, i.e. L equals 1, with spin-half electrons. So just an elementary Clebsch-Gordon exercise will give you these 4 spin 3/2 states, from plus 3/2 down to minus 3/2 here. So what happens now when we place an atom in a crystal? Well, typically the energy levels of the isolated atom, as we've seen, can be characterized by this J quantum number. But once we place the atom in a crystal, the crystal fields will typically quench the angular momentum, And so essentially we lose the information about this L, and we end up with effectively spin half block electrons. However, if we have a sufficiently high symmetry, which is realized in cubic materials, we cannot completely quench the angular momentum of J equals 3/2 levels. And so we can obtain, in some cases, essentially spin 3/2 block electrons. Now, it turns out that this has actually been known now for many, many years. So the first people to realize this and to write down a Hamiltonian for these electrons was Luttinger and Kohn in 1935. So here we have a rather complicated form of the Luttinger-Kohn Hamiltonian, which is written in terms of J equals 3/2 spin operators. However, we can get a bit of more insight into this if we make the condition that this parameter gamma is equal to this parameter beta, in which case the Hamiltonian is now spherically symmetric. And what we find are that the eigenstates of this Hamiltonian are essentially quadratically dispersing states, which are touching together at the center of the Brydon zone. So at the center of the Brydon zone, we have a fourfold degenerate state, whereas away from the center of the Brydon zone, we split off into these two quadratically dispersing bands. Importantly, from the form of this Hamiltonian, we can see that this k dot j term commutes with the Hamiltonian. And so that means that we can essentially, we can equate the eigenstates of k dot j, or the Hamiltonian and k dot j can have simultaneous eigenstates, so spin half and spin 3/2. Now, this is observed in many materials, such as gallium arsenide. We have the gamma-8 band, and in yttrium, platinum, bismuth, we also have a gamma-8 band corresponding here to our spin 3/2 manifold of electrons. So now let's go ahead and construct the gap function for our spin 3/2 electrons. So using our fermionic antisymmetry, we are required to essentially distinguish between even angular momentum spin singlet, or now spin quintet states, or odd angular momentum spin triplet or spin septet states. So that is, we can now have pairing into a total spin angular momentum state of up to J equals 3. Now, you're going to be relieved that I'm not going to go through all of these states, but rather I'm going to focus my attention on the singlet and the quintet states. So let's start by thinking about S-wave pairing. So the simplest possible way we can pair electrons with the spin 3/2. And a bit of an, again, a Clebsch-Gordon exercise, we can write down our wave function here as an relative S-wave in our angular momentum state, and now a spin singlet, essentially a J equals 0, JZ equals 0 state here. And we can also now write down 5 J equals 2 spin quintet states, which makes for a very pretty picture. But essentially, these are all, again, superpositions of J equals 2, MJ equals 0, 1 to 2 states. So having written down these states, we might ask the question, what would the gap look like at the Fermi surface? Surely all of these states will give us just an S-wave pairing state, just give us a full gap, as we have come to, as we might have expected if we looked at us in our spin 1/2 theory. But this is not quite so simple now. To understand that, let's have a look at the pairing gap, or the gap along the Z direction. Now, because we're dealing with our rotationally symmetric Luttinger-Kohn Hamiltonian, we have that the states that are curving upwards here in the red band are essentially spin 1/2, plus 1/2, minus 1/2, while the states in the band curving down are spin 3/2. And we want to open a gap here around the chemical potential, around the Fermi energy mu. Now, if we look at the singlet state wave function, we see that this is not going to be a problem, because there is always a matching spin state available for pairing. So here, in order to open a gap around the chemical or the Fermi energy in this picture, we need to pair spin -3/2 with spin +3/2. And indeed, such a state exists in our wave function. So that's great. And it means that actually we can open a full gap here. However, if we take one of the quintet states, we find that something very interesting has occurred. That in this particular quintet state, we cannot find a partner state. So here we are always pairing spin +3/2 with -1/2 or +1/2 with -3/2. And there is, we don't have a partner state available to us close to the Fermi energy. And so there will be no possibility to open a gap here. So in other words, we have a node coming, even though the angular momentum state of our Cooper pairs is S wave. So it's interesting here to actually draw an analogy between the spin half pairing picture and the spin 3/2 pairing. In the spin 1/2 pairing, the gap at the Fermi surface is essentially expressing the orbital angular momentum of our Cooper pairs. But for the spin 3/2 pairing, the gap at the Fermi surface is expressing the spin angular momentum of our Cooper pairs.
Ask another question.
Yeah.
So, if there is no state for the pairing, what is the intuition that the state will be energetically favorable at all?
Well, that's only in this particular direction. That's only in the direction along the z-axis. But in other directions, such pairing states will exist. And essentially, you will be able to open a gap.
Oh, I see. Thank you.
So here, in this particular quintet pairing state, which I just illustrated along the z-axis, you can see that there is actually a node along in the direction along the kz axis. But if we move away from there, we find that we can open a full gap.
I see.
So what this is telling us is the first important lesson, and that is in the presence of spin-orbit coupling, the gap at the Fermi surfaces is controlled by both the orbital and the spin angular momentum of the Cooper pairs. Okay, so now let's move along and talk about spin-polarized quintet states. So if our intuition holds, just as if we threw away one of our, if we throw away one of these Cooper pairs, the Cooper pair involving spin -3/2 pairing with spin +1/2, we should have essentially a spin-polarized pairing state. And based on our intuition that we have that essentially the gap at the Fermi surface should represent or somehow give us information about the spin angular momentum, we expect from, again, simple spherical harmonics that we should have something like the gap should be somehow related to the spin 2-1 spherical harmonic. So in other words, what we expect to see in our nodal structure is shown here in this picture here. We have a line node in the equator and point nodes at the poles. And if we look at the excitation gap here, so what I'm doing is I'm going along essentially the angle with respect to the z-axis and looking at the gap, we see that this is indeed accurate. We find our point node here at theta = 0 and our line node here down at the equator. But this picture here is essentially calculated in the limit where delta is very, very small. So what happens if we make delta a bit bigger? So we see something a bit surprising happen. We now see that there is actually a region here around the pole and around the equator where we have actually zero energy excitations over a range of theta values. And as we increase delta, this becomes larger and larger. This is actually quite a shocking result. because it's telling this particular direction, this angle phi that I've chosen isn't anything special. I could get the same result if I looked in any other direction. And now, instead of point nodes, we have some extended region, point or line nodes, we have an extended region where we have a vanishing excitation gap. So in other words, we expected to get this picture, but what we have obtained is this, that essentially you can imagine that we have somehow inflated our Fermi surfaces, our point or line nodes into Fermi surfaces, into, in fact, two-dimensional surfaces in our three-dimensional space where the excitation gap in the superconductor is vanishing. And we've christened these Fermi surfaces the Bogoliubov Fermi surfaces. Now, at this point, I should say that one might object to this on the basis that perhaps I have just fine-tuned my system. Perhaps this is just a particular fine-tuning, and if I add something to my system, I can make these Fermi surfaces go away. But it turns out that we can't do that. So the argument here is rather complicated, but essentially there is a topological obstruction to getting rid of these Fermi surfaces. So essentially we can think about it as the square root of the determinant is changing sign as we go from the outside of the Fermi surface to the inside. And we cannot get rid of that we cannot eliminate that sign change by adding any symmetry preserving perturbation to our system. So in other words, our Bogoliubov Fermi surfaces are not fine-tuned. They are actually a generic feature of our system. So what is the origin of these rather remarkable electronic structure? So to get some understanding of this, we write the Hamiltonian in a band basis. So we involve here in the upper block, we have pairing between electrons in the plus band. In the lower block, we have pairing between electrons in the minus band. And in these off-diagonal blocks, we have essentially an interband pairing potential. So our first approximation is the simplest one that we could think of, and that is, let's just project into the low energy state. So let's throw away everything else except for this block here in the lower right-hand corner. And we essentially arrive at an effective single band model. But it can be quite easily shown that this effective single band model can give a superconducting state, which is only going to give us line or point nodes. It's only going to give us something that we would have had if we are dealing with spin half electrons to begin with. So what that is telling us is that we've thrown away too much of the Hamiltonian. In other words, the Bogoliubov Fermi surfaces must arise from the interband pairing. They must, this off-diagonal part here, which couples the plus and the minus bands together, must be somehow important for the superconductivity. And we can include this perturbatively. So by essentially a simple second order perturbation theory, we find that we introduce a correction to the normal state Hamiltonian. There is a chemical potential shift, which is basically pretty uninteresting. But the very important and relevant point here is that we get something that looks a bit like a magnetic field appearing. We call it a pseudomagnetic field. So in other words, we are lifting this, the degeneracy of the band electron states here due to this interband pairing potential. And this is only appearing if we have essentially a spin-polarized Cooper pairing in the system. So essentially, this is essentially a low energy of, we can solve this problem of a magnetic field and a pairing potential, and we in fact get exactly what we expect. The pseudomagnetic fields shift the nodes to non-zero energy, opening a Fermi surface. So if you are, anyone in the audience is perhaps familiar with, more familiar with cold atomic gases, this scenario is very similar to so-called breached pairing in a spin-polarized cold atomic gas. But here the Fermi surfaces are not coming extrinsically from essentially forcing a large spin splitting on the system, but rather they are appearing intrinsically to the superconducting state. And I'm afraid to say I had a picture here that I was going to show you, but it doesn't appear to want to turn up. But as our perturbation theory gives us some very important information on the dimensions of this Fermi surface. So in particular, in the direction perpendicular to the normal state Fermi surface, these Bogoliubov Fermi surfaces will be actually rather thin, but parallel to the Fermi surface, they will be able to extend much further. So you might be asking yourself the question whether or not the this J = 3/2 spin was really a necessary requirement. And if so, this is a very specialized problem, which is probably of very little relevance. But it turns out that we can make an argument that, in fact, this is actually much more widely valid. So the 5 non-trivial matrices which appear in the Larginger-Kohn model can be parameterized as shown here. And if you are keen on some algebra, you can show that these matrices are essentially anti-commuting with one another. So that is, they are maybe more technically a representation of Euclidean direct matrices. So what that means is that by unitarily transforming these matrices, we can essentially map the problem to Kronecker products of 2 Pauli matrices. And we might decide to regard one of these Pauli matrices appearing in this Kronecker product as essentially some kind of orbital degree of freedom, and the other to be the spin degree of freedom. And this would give us essentially a generic and general 2-band model of electrons in a solid state system. So indeed, shortly after we published our paper on the Bogoliubov Fermi surfaces, Dužek and Sigrist, working in a spin 1/2 picture, showed that in fact they also could obtain Bogoliubov Fermi surfaces appearing in a generic 2-orbital model. So in this particular model here, they would have expected to find point nodes at the tips of these Fermi surfaces, but these point nodes have been inflated into spheroids, so the Bogoliubov Fermi surfaces. And from this, we draw a very important conclusion that in any even parity superconductor, where time reversal symmetry might be broken, we must generically expect that point and line nodes will be inflated into Bogoliubov Fermi surfaces. So these Bogoliubov Fermi surfaces are not some kind of peculiarity of a spin 3/2 physics, but rather completely generic feature of multiband superconductivity. So how would we go about evidencing the existence of these Bogoliubov Fermi surfaces? Well, because they are a Fermi surface, we would expect characteristic thermodynamic power laws similar to that in the normal state. So for example, the heat capacity or the thermal conductivity or the nuclear magnetic relaxation rate would all be essentially proportional to temperature at very low temperatures. Now, remarkably, such contributions are not seen too uncommonly in unconventional superconductors, although usually these contributions are interpreted in terms of impurities. So just to give you an example here, in the thermal conductivity of uranium ruthenium to silicon-2, you can see that kappa over T as a function of T squared will converge to a finite value as the temperature goes to 0, which is telling you that there is a linear in T component of the thermal conductivity, which could be perhaps interpreted in terms of a Bogoliubov Fermi surface. And indeed, uranium ruthenium to silicon 2 is an ideal candidate material. Previously, people had suggested that the gap structure should have this line node and point node combination that we had seen earlier. And we might propose that perhaps actually what we are seeing in this material is something more like this picture rather than the picture that people had proposed earlier. So at this point, I suspect that I'm running pretty close to the hour. So although I had hoped to tell you something about strontium ruthenate, I'm not sure if this is really the best forum to do so. Mira, do you have any comments on that?
Well, maybe, well, there are a few questions appearing in the chat. Maybe it would be good to cover those first, and then if people are still interested, we can.
Yeah, that sounds good.
Yeah.
That's okay. So, oh, I have quite a few questions. Sorry. Okay.
No, it's just yeah.
Okay, so so Alexander, you asked, can we close this splitting and kill the Fermi surfaces with a magnetic field? That's an excellent question. We would then, the problem there is that we would then have to start accounting for something such as effectively orbital effects, which might be very difficult to do. Though typically the pseudomagnetic field will not necessarily point in a nice direction or single direction in space or in the momentum space. It might be essentially winding around the Fermi surface. And so it could be very, although you might be able to gap out parts of the Fermi surface by applying a Zeeman field, you might not be able to gap out the other parts. Now, Jesper asked, can these Bogoliubov Fermi surfaces be fine-tuned to merge? Okay. Yes, but I don't think that wouldn't necessarily kill them off. One could always imagine somehow it would be possible to add some kind of perturbation to the Hamiltonian, which could essentially start to move this Fermi surface down towards the ring, and we could essentially combine this Fermi surface with the ring itself. But we are not going to kill off the Bogoliubov Fermi surfaces in doing that. So the topological charge of the Fermi surfaces will be essentially preserved during this merge. We're not going to have some kind of annihilation. And Oliver Bleu. So the delta plus minus pairing mediated by lattice vibrations. Okay, so I've been, I have to say that I've been completely silent here about the pairing interaction. I'm essentially leaving this as something for other people to figure out. But the question essentially might be, well, we would, so thank you, Richard. Anyway, so the question might be is that we would canonically expect in the BCS theory that we only have an attractive interaction within a small range of energies about the Fermi energy. And so that would seem to essentially preclude this delta plus minus. However, for example, something like the Coulomb repulsion is still active between electrons with different energies. So, and this Coulomb repulsion, although it is repulsive and pair breaking for the superconductivity, it can still mediate the formation of a gap, as was pointed out by Anderson and Morel back in the 50s. So we could have something like this delta plus minus here coming from an Anderson-Morel type mechanism. But maybe more generally, we can also regard the delta plus minus as something of a matrix element effect, that we are getting this when we project the superconductor, or when we express the superconducting pairing potential or the wave function in the band basis, we find that there will be components which pair electrons in the same band and pair electrons in different bands, simply due to the matrix elements of in our system.
All right. Maybe should we stop? Any more questions now? For any further questions, people want to raise their hand or speak up or put it in the chat.
So Philip, one more question. If you start to take your bulk material and now make it thinner, or you apply strain so that you break the degeneracy at k equals 0.
Yep.
Will that kill this superconductivity?
No, not I've developed this theory here today in the context of a Lutton-Jacone model of a bulk spin 3/2 system, because in some sense it's historical. That's how I came to it. But what we discovered later is that in fact this is essentially generic to any system where we have somehow two bands which are coupled via spin orbit coupling to one another. So in the context of what maybe you're thinking about, if you take a semiconductor and you, with one of these Lutton-Jacone Hamiltonian, if you take one of these semiconductors like gallium arsenide, and if you were to deform the material in such a way as to break the cubic symmetry, you will split the, lift the degeneracy of these states at the center of the Brydon zone. But essentially, that is essentially a detail. It's not important for our theory.
Okay, thanks.
Any further questions? Actually, I was wondering, Philip, yeah, so maybe since it is getting a little bit later, I mean, can you summarize very briefly what you wanted to say at the end, or should we just do it for another?
Sure. Sure.
And then
wrap up. This, okay. I think, is the best summary I can give for my talk. Okay. That we now have 4 superconducting gaps. We have the full gap, the line nodes, the point nodes, and now we have the Bogoliubov Fermi surfaces. And with that, I'd like to thank you very much for attending this Zoom colloquium.
Okay, thank you.
I have another question, actually, one more. So what about 2D?
Okay, excellent question. Well, you can't really, I guess in 2 dimensions, you can only really have point nodes or a full gap in the usual way of thinking about things, right? So in the context of 2 dimensions, a Fermi surface would be essentially a line node. But I think that this would be possible. I think this would be entirely possible. You could imagine that your point nodes on your 2-dimensional Fermi surface start essentially inflating up into true Fermi surfaces. And indeed, there is some proposal that this might even be realized in an iron selenide material, I think from the Hirschfeld group. Dimitri?
So you have, for example, you have px plus ipy is fully gapped. Px yes. And py, they have a node, just 1 point, actually 2 symmetric points.
I think it would be
they will blow out in this similar way.
Yeah, I think, look, I think you're right. I think it would be very difficult to actually, for this to occur in 2 dimensions, because most of the gap functions that could give rise to a Bogoliubov Fermi surface would probably already show a full gap in 2 dimensions anyway. But in principle, if one wants to start playing around by combining gaps with wildly different symmetries, you could perhaps get Bogoliubov Fermi surfaces. One can imagine this, but I think it's much less likely than in 3 dimensions.
Okay, thank you.
Thanks. Olivia has a question. Olivia?
Yes, thank you very much for your talk. I have another question. I think it's a very naive one, but at the beginning you mentioned conventional superconductor, and I was wondering, is there a definition? What is a conventional superconductor? Does it mean that this is BCS-like, or it is something else?
I would say it's essentially based on the BCS theory or its strong coupling extensions. So essentially, pairing is mediated by electron-phonon interaction, and that we end up with the S-wave spin singlet pairing Cooper pair wave function.
Okay. So most of what you have shown us today correspond to unconventional superconductor. Okay.
Exactly. Which is where the fun is, because we don't understand how they work generally. So
I see. Thank you.
Yeah. Any further questions? Actually, sorry, one last question then. So what about pairing at finite momentum?
okay. So FFLO type states. I think that this could give this in principle could give rise to a Fermi surface indeed, but this is essentially a rather strong deviation from the superconducting. This is a rather strong deviation from the conventional picture of a superconductor. So it's a superconductor under quite extreme conditions. And I would say that the nodal classification of the usual nodal classification here, which we've extended of point nodes or line nodes or a full gap, is in reference to essentially a pure superconducting state with no applied fields. And in fact, what we've attempted to show here, or what we hope I've demonstrated, is that in fact you get this also with the, you can also get a Fermi surface in these conditions as well.
Mm-hmm. I was just wondering if even in your setup, whether you could get something, I mean, you said yours was analogous to a breach pairing or pairing within like some effective field. Could you also get something that was FFLO-like even in this situation?
We haven't really, I mean, we haven't, it's a good question. We haven't really examined FFLO or pair density wave type solutions extensively, but I see no reason why we couldn't have that.
Okay, great. All right, so I think we should call it call it a day. Yeah. Thanks, Philip, for a really nice talk, and yeah, maybe we can talk in person at some point.
Okay.
Yeah.
Thank you very much.
Yeah. Okay. Bye, everyone.
Thank you, Philip.